today with Chapter 1. So I just want to remind you guys that there is no physical textbook for this course. If you go to our Power School page and you go to our trig class, you'll see that I've posted the things that we did on day 1. And what I'll do for the textbook is I'll post the materials kind of each time we start a new chapter. So all the Chapter 1 stuff is here. So the lessons are like the book pages. The problems are the homeworks that we're going to be doing. And the odd solutions are obviously the odd solutions to the homeworks. So the stuff I'm going to be talking about is going to come from sections 1 and 2 from the lessons handout today. And the homework you'll work on are the problems from the problem sheet. Everybody okay with that plan? Okay. So let's get us started here. So the first section here, section 1.1, is all about functions. So you're going to find that this first chapter for trig is going to feel pretty similar to the first chapter from Algebra 3.4. It's very much along the same lines, but we'll talk about many of the same things. We'll look at some techniques that are a little bit more advanced on how to deal with some of these topics, and look at things in a slightly more in-depth way, but a lot of the material or the things we're going to look at are going to be pretty similar. Okay? Good. So let's start with a definition here, and we'll start by defining a function. So we say a function from a set D, we call that set the domain, to a set R, we call that set the range, is an assignment such that every member of the domain pairs with exactly one member of the range. And it's this exactly one part that's the important part for our function definition. Hopefully this sounds pretty familiar, that you kind of remember this definition now if you hear it again from last year. We spent a lot of time in first semester of Algebra 3.4 talking about functions and what the definition of a function was. Right? That start hopefully sounds pretty familiar. Yeah? Maybe? Probably? Hopefully. Also, hopefully you remember, there were several different ways that we had to represent a function. Does anybody remember the different ways that we could represent a function? One of the ways? I think there's 5 of them, so there's a lot of choices here. Anybody remember one? This would have been the very beginning of the year. Table. Okay, an XY table, absolutely. So that's definitely a way that you could represent a function. Good. Now that we got the first one down, does that help open the floodgates for anybody else? if you're not sure, you can still take guesses. There's no penalty for wrong answers. I promise, unless you're Caitlin, I probably won't make fun of you. A graph is a good one. Yup. Good job taking the risk. Domain and range are ways to describe a function, and we'll be talking about those later in this lesson. So you're on the right subject, but not quite what we're looking for. I think what you're talking about is called a mapping diagram. Or you'll say yes anyways, even if you don't remember if that was actually the name for it. But that is another one. I think there's two more. Good, an equation. Yup. So like y equals x squared or something would be another way to represent them. And then the last way, similar to an XY table, we would say is a set of ordered pairs. Oops. Maybe I'll just say set of XYs. I don't need to say ordered pairs. We'll just say a set of XYs. Does that jog a little bit of memory here? We'll do some examples looking at each of these types. So if you're still like not really sure what some of those things are, that's okay. So let's look at some examples. So if I'm looking at an XY table here, is this representing a function? So our definition has two components. So it says we need to make sure every member of the domain has a pair. So which part is our domain, x's or y's? That's the x's. So do all the numbers here have a y that pairs with it? Okay, so we satisfy that part of the definition. The second part says that pair has to be with exactly one member of the range. So I have to make sure that each x is only paired with one y. So if I look at -1, that pairs with just 7, right? -1 doesn't pair with anything else. If I look at 0, that pairs with just 2. 0 doesn't pair with anything else. If I look at +1, that pairs with just 3. That's good. 2 pairs with just 5. And 3 pairs with just 7. So this satisfies our definition because every x is paired, and each of those x's is only paired with one y. Now notice that it didn't matter that one of the y's was used more than once. Really all we care about is that all the x's are used and none of the x's are used more than once. Everybody okay with that idea? Okay. What did we say next? A graph. Now we had a special method that we talked about last year to determine if a graph is a function or not. Does anybody remember what that method was? The vertical line test is what we used. And what the vertical line test says that if I can draw any vertical line that intersects the graph more than once, then that graph does not represent a function. So in this case, is this a function? Is the one that I've drawn a function? Yes, right? No matter where I draw that vertical line, it's only going to intersect the graph one time. So that's definitely a function. What would it look like if it was not a function? So imagine something like this. Here, if I try to draw a vertical line, there are several vertical lines I could draw that intersect the graph more than once, right? Do you guys all remember using the vertical line test last year? This tends to be the one that students remember the best. The visual, I think, helps make it a little bit easier to use, right? The next one you guys mentioned was a mapping diagram. So if you don't remember what those look like, we have one oval. The first oval usually represents the domain. And then we have a second oval. That second oval usually represents the range. And then inside of each of those ovals, we'll have the members of that set. And then we'll draw some arrows showing which x's pair with which y's. So the mapping diagram I've drawn here, is this a function? Yes, right? All the x's are paired with just one y, so that is a function. What if I have this? Is this a function? No. Why not? Great, because 4 doesn't pair with anything. So we have one member of our domain that doesn't have a pair. So this is not a function. What if we have this? Is this a function? Yes, this is. So are all the x's used? Do all the x's go to just one y? Yes. Does it matter that some of the y's are not used? No. Does it matter that some of the y's are used twice? No. This is still a function. All the requirements for the function are on the x's. So the x's are really where we got to check. What if we have this one? Is this a function? No. What's wrong with this? Very good. So 1 is paired with 2 different y's. Do you guys feel good so far about determining whether these different things are functions or not? So far, so good? Hopefully you remember a little bit of this. We spent a good amount of time in first semester doing these kinds of exercises. So hopefully that's coming back to you. Next, I'm going to skip equations for a moment because that tends to be one of the more difficult ones, and go instead to our sets of ordered pairs. So we have the ordered pairs 2, 6, 3, 10, 611 and 28. Is this a function? Okay, why not? Yeah, so the x value of 2 repeats. Now, if this instead had been, the last ordered pair had been 8, 2, would it be a function? If the last ordered pair was instead 8, 2 instead of 2, 8, that's a function then, right? Good. All right. All right. Let's say we have the equation y equals x squared plus 2. Does this represent a function? Well, you should recognize something that looks like y equals x squared plus 2, right? This looks like something we would have covered last year, right? What is the shape of a graph going to be for something like this? What would this graph look like? This should be something that you can look at and know what the shape of the graph would be. What kind of thing is this because of it being x squared plus 2? Okay, good. So the shape of the graph is a parabola. We would call this quadratic. So I know that if the graph looks like a parabola, is this going to be a function? Yes. So these things that you recognize from Algebra 3-4 from last year, all of those things that we talked about were functions. So if you see something you recognize, that's usually a good instance. But what happens if instead of y equals x squared, what if we had x equals y squared? Yeah, so that's going to look, like this, right? It's going to just turn it to the side. Is this a function? No. This was a function. This was not. Okay. So the general rule that you should be suspicious of, if something has a y, kind of all by its lonesome, and there's nothing else kind of weird going on in there, like you just see normal things that you've seen in Algebra 3-4, you're probably looking at a function. If you see something going on with the y, though, like a y squared or a square root of y or a plus or minus y, those are all indications that we need to be a little bit careful and think about exactly what we have here, because it's very possible you have something that's not a function. So if something's kind of happening to the y, other than like addition and subtraction, it's very possible you're looking at something that's not a function. But let's do a couple more examples, okay? Let's say we have y equals x plus or minus 1. Kendall, you mumbled something. What did you? Can you repeat it for us? Okay, you think it's not a function, right? Why? No, I think your instinct was correct. So Kendall initial thought was this wasn't a function. That is correct. This is not a function. Now, it seems contrary to what I just warned you about because you have the y by itself, right? What else, though, is kind of funny going on in here? We usually don't see equations with plus or minus written in them, right? That's not very common. What would happen if, say, we picked a value for x and tried to make an xy table here? So somebody pick a value for x. 2. Okay? So if I plug 2 in, I'd get 2 plus or minus 1, right? If I evaluate 2 plus or minus 1, if it's 2 plus 1, I could get 3. And if it's 2 minus 1, I would have 1. So that's saying that I have 2 separate y values for the x value of 2. Is that a function? Not a function, right? Because we have one x with more than one y. So if you're unsure, one of the things you can do is if you get the y by itself, you can try picking x's and plugging them in and seeing if you get multiple y values. If we go back to this problem from before, say I try to get the y by itself by subtracting that 2 over. And then to get rid of the squared on our y, what would we need to do? Square root both sides. But remember, what happens when we square root both sides of an equation? We get a plus or minus. And now all of a sudden it should be relatively easy to see that you're going to get, if you pick a single x, you're going to get 2 results because of that plus or minus, right? Just like what happened before. Did you guys notice that? So those are the kinds of situations, at least for an equation, that you'd have to worry about. The only other thing I can think of that would be a reasonable expectation would be something like this. What do we think here? Well, let's see what happens if we try just picking a value for x and figuring out what the y's are. Sound good? When in doubt, this is a good thing to see, a good check to make. So let's pick a value for x. 4. Lovely. Okay, when I plug 4 in for x, I get 4 plus the absolute value of y equals 3. And if I subtract 4 from both sides, I get -1. And right now, what do you notice here? Does this have a solution? Why not? The absolute value of a number cannot be negative, right? The absolute values are always positive. So what that means is we just picked a bad value for x. So we should try picking something else. So should I pick something smaller than 4 or bigger than 4? Look at what we did here. Smaller, okay? 2, lovely. So if I subtract 2 from both sides, I get the absolute value of x is equal, or absolute value of y is equal to 1. Everybody okay with that? Okay. What can I take the absolute value of that gives me positive 1? I could use 1 or -1. So is this a function? No, because we have one x with two y's. So if you see something funny, try making an xy table, and if you get more than one y value for a given x value, it's not a function. Everybody okay with that? Okay. The equation ones tend to be the most difficult ones. Why I spent the most time there. It's also one that we didn't spend a lot of time in Algebra 3-4 doing those kinds either. Right? We focused mainly on the other situations. What I want to do next is talk about function notation. So what we mean by function notation is it means we're using f of x's instead of y equals. Yes, Jess? Of course. So what we're saying is if I have something like y equals 3x minus 4, I could use that interchangeably with something like f of x equals 3x minus 4. That either one is fine. We're just going to use those two symbols kind of interchangeably. We have a special name that we give to each of these variables. We call x the independent variable, and the y is the dependent variable. Or similarly, the f of x is the dependent, and the x is the independent. Just to be clear what I'm pointing at there. And hopefully that vocabulary sounds familiar. We call x the independent variable because we can choose whatever we'd like for x, right? We call y the dependent variable because to calculate y, we need to know what x is. So that's the gist of that. Everybody okay with that idea? Okay. This is a relatively old topic that you would have seen many times by now, so we're not going to go too much in depth there. Next section, we're going to talk about domain and ranges. And in this class, when we write our domains and ranges, we're going to use interval notation to do that. So let's spend a few minutes here talking about how we move from an inequality and write that instead as an interval. So let's say we have the inequality x is less than 2. So if I look at x is less than 2, to write the interval for this, I need to start by determining what the lower bound is and the upper bound is for the values that are less than 2. What's the lower bound on the values that are less than 2? What's the smallest value there that you could be talking about? It feels like there's not a number, right? So we would say negative infinity. Exactly right. Does everybody agree with that? that if you're talking about the numbers less than 2, that goes on forever in the negative direction. So the symbol we use there is negative infinity. What's the upper bound in this situation? 2. That's the biggest value that you could be concerned with. So I'm going to have my lower bound on the left and my upper bound on the right. I always write lower bound on the left and upper bound on the right. It should always be going from small to big. Okay with that? Next thing we need to do is indicate whether that lower bound or upper bound is included in our interval or not included in our interval. So let's start with the lower bound. That's negative infinity. Can we ever arrive at negative infinity? No. So should infinity or negative infinity be included? No, because we can't actually get there, right? So the symbol we use for something being not included is the parenthesis. Now let's look at the upper bound. Is positive 2 included in x is less than or equal to 2? Yes. Why? Because it's a less than or equal to. 2 is definitely less than or equal to 2. So the symbol we use there is a square bracket to indicate that 2 is included. If you remember back into our Algebra 3-4 course, most of the time we wrote domains and ranges, I used interval notation, although I accepted a variety of notations in Algebra 3-4. We'll be a little bit more specific here in this course and look for specifically interval notations when we do this. So you should be able to write these. So let's write the interval for negative 5 is less than y is less than or equal to 10. The first thing we want to do for this is determine the lower and upper bounds. What's the lower bound? Negative 5. And the upper bound? 10. Everybody feel good about that? Is negative 5 included or not included? So if I look at the inequality, it's a strict less than, so it should be not included. So do I use a parenthesis or a bracket? Parenthesis. Let's look at the upper bound now. Is that included or not included? Included, because it's a less than or equal to. So should I use a bracket or a parenthesis? Bracket. Now, if I just write down these two intervals without any context, it's difficult to determine which one would be talking about x's and which one are talking about y's. You notice specifically the first interval we wrote is referencing x's, and the second interval is referencing y's. Did you guys notice that? So we're going to include a little bit extra notation so that if I were looking at this on a sheet of paper, I knew which one is referencing the set of x's and which one is referencing the set of y's. So to do that, I'm going to put an x, and I'm going to use this little symbol that looks like a curvy capital letter E. This symbol stands for the phrase is a member of the set. So for this second interval, instead of writing x is a member of the set, I would write y is a member of the set. because this one is referencing y's. Likely I would not be very picky about this on a test setting, but you'll see it in the homework, in the answer keys, in the book pages. So I just want to make sure that we're familiar with that little bit of notation there so it's not confusing when you get to it or you come across it, okay? Everybody feel okay so far? There's one more example for writing something in interval notation that I want to show you guys. And that's if the situation involves an OR inequality. So I think we've touched on this briefly last year. Does anybody remember the symbol that we use to deal with an OR? It's like a U with no tail. This is the symbol for union. In set speak, that's the same thing as an OR. So we're just going to write this as two separate intervals that we're going to connect with this union symbol. Now that I write this, does this look familiar? You remember seeing this last year, I hope. We used it on occasion. It wasn't very frequent. The fact that nobody could really come up with it is not surprising. It's okay. So we'll look at these each independently. If I look at a is less than -2, how would I write the interval for that? Well, let's start with the lower bound. What's the lower bound for a is less than -2? -infinity. And the upper bound then is -2. Is the -infinity get a bracket or a parenthesis? Parenthesis. Does the -2 get a bracket or parenthesis? Parenthesis. So all the infinities get parentheses, and because it was a strict less than symbol, the -2 gets a parenthesis also. Let's move on to the second part. A is greater than or equal to 5. What's the lower bound for a is greater than or equal to 5? 5. And the upper bound is positive infinity. I put a plus sign in front of the infinities when I write positive infinity. You don't need to do that for positives. I like to do it just to keep everything straight for myself. You do need it a negative for a negative infinity, though. The 5, should it be a bracket or a parenthesis? Bracket, very good, because it is a greater than or equal to. And then the infinity gets a parenthesis. The infinities always get parentheses. And then to indicate that we're talking about this a variable, we'll just put that a as a member symbol, just kind of slide that in front. Any questions about interval notation and using that? So kind of from here forward, if we're writing a domain and range, the expectation is that you're going to be using interval notation as our primary tool to do that. Okay? So next up, we're going to talk about domains. Okay. So, in general, when we talk about domains, at least for, this beginning part, there's really two operations that we have to be careful about. So there are two things that we've done where you can, or that we've done commonly. We've done use these operations a lot. Even prior to last year, we used them quite a bit. That can make the function undefined. Those two things are square roots and division. When is a square root undefined? When can't I take the square root of a number? What kind of numbers? What? If it's negative. When do I have trouble dividing? Or when is a fraction problematic? When the denominator is 0. Right? What happens if you try to divide something by 0? It is not 0. So this is a common misconception. So think about division like really naively. So the denominator in division is basically how many piles you're dividing your thing into. So if I did like 8 divided by 4, I want to split 8 up into 4 separate piles. How many things would be in each of those 4 piles? Would be 2, right? If I take 8 and try to split it up into 0 piles, does that make sense? No. If I take 0 and I try to split that up into 8 piles, that's still okay, right? I would just have how many things in each pile? 0. So 0 in the numerator of a fraction is fine. It's just 0. If I have 0 in the denominator of my fraction, that does not make sense. That is undefined. Does that make sense if we kind of unpack really what division means again? I know it's been a long time since you probably thought about division in that fashion. Okay. So we said square roots are a problem if we're taking the square root of a negative number, right? That's what Hannah said. So to figure out the domain for something like this, I'm going to take everything that's underneath the square root, and I need it to be non-negative. That means greater than or equal to 0. Everybody okay with that? Those are the values of x that I will be able to take the square root of in this function. So I'm just going to add 4 to both sides. And that's my domain. To just write this now, or the last thing I'm going to do is just write this in interval notation. So x is greater than or equal to 4. The lower bound is 4. The upper bound is infinity. The 4 gets a bracket because it's a greater than or equal to. And the infinity always gets a parenthesis. Everybody okay here with that first part? Our next example, is there a square root going on in here? No. Is there division? Yes. Where's the problem with division? It's if the denominator equals 0. So let's say the denominator can't equal 0. Because that's the thing that's a problem. Everybody okay with that idea? if I solve then, I can subtract 2 from both sides, and I have x is not equal to negative 2. But this is not going to be easy to write in interval notation. I need to really convert this into an inequality. So the trick to do this, if x cannot equal negative 2, x could be less than negative 2, or x could be greater than negative 2. Everybody agree that that covers everything except for negative 2? That's a sneaky little trick. You probably wouldn't have come up with that having not seen it. Once you've seen it, though, it shouldn't be a big deal. But coming up with that on your own would have been, maybe took a little bit of inspiration. Now that I have it written as an inequality, though, I can write this using interval notation. So the first part, the lower bound is negative infinity, and the upper bound is negative 2. Infinities always get a parenthesis. And the negative 2 is going to get a parenthesis because it was a less than symbol. Where the or is, I'm going to write my union. And the next interval, the lower bound is negative 2. And the upper bound is positive infinity. The negative 2 gets a parenthesis because it's a strict greater than. And the infinity always gets a parenthesis. Is everybody okay with that idea? Okay. And our last example is V of S, where, or V of S equals S cubed, where V of S is the volume of a cube with side length S. So when I talk about my domain, which variable am I talking about, S or V of S? Which one is the independent variable? Which one goes with the domain? S. Okay? What is S representing? A side length. So what values should S be limited to? What are you looking for? Yep. So what values is S limited to if it's a side length? Just 1 second. Let's answer this question. It's a side length, right? What? Okay, you're real close. Can't be negative, right? You could be less than 1 still, but it has to be greater than 0. So we would say that. Please check Power School tonight. I'm going to have a short assignment for you guys.